Okay, welcome everyone. This is our first PIES webinar, right? PIES here stands for the Physics Innovation and what was it about again? Physics Innovation and Exploration. That's right. Physics Innovation and Exploration series. Of course, it's easier to remember PIES. In a couple of days' time, okay, maybe 3 days' time to be precise. It's we celebrate Pi Day International, right? But for now, hope you're enjoying your start of the March holidays, at least for those students who are in Singapore. My name is Darren. I'm from the Ministry of Education. And really today we are very happy to have a very brilliant young physicist, Tan Myn Jae, who will be talking to us about this really interesting optics experiment. Let me give you some introduction to Myn Jae first. Right, Myn Jae is currently a year 5 student in Hwa Chong. Right, he actually represented Singapore at this online young physicist tournament last year. Right, so as part of this, it's a bit of a debate style competition, and he will sort of use some of the projects he's worked on to share with us today as part of this PIES webinar. Right, so of course the OYPT, this young physicist tournament competition is a bit intense, right? It's a debate style kind of competition, but today it's more relaxed, right? We have a more informal sharing. He can take more time, explain things, and really we also want to hear from you. As and when you have questions, please just raise your hand. You know, Zoom has this raise hand function, right? And then we will try to sort of clarify, because these are not easy things, right? But very interesting things nonetheless. We will also be able to use the chat, right? So feel free to start typing things in the chat as and when, and then we can try to pick up from there. Of course, Myn Jae will be focusing on his presentation. I can sort of monitor the chat and try to answer things if I think I sort of know how to answer it. What else should I say? Yeah, so Myn Jae, again, he's a year 5 student. He takes like many of you probably, PCME, right? So he physics, chem, math, and econs, right? As his combination. And I understand from his bio that he enjoys Mendo pop as well. So not sure how many of you are into music. Of course, Taylor Swift has come and gone. Possibly some of you have gone to the concert, not me, but of course everyone in Singapore probably knows about it by now. And what else should I say? Okay, maybe just a brief introduction to, okay, and okay, just to be clear, we are recording this webinar just, you know, so we can consider the possibility of sharing this later on, so hope you don't mind. In terms of the problem today, let me not take up too much of the time because I'm sure you're all excited to hear what Myn Jae has to share. Just if you look at the slide that he's sharing right now, right, it's really this very interesting phenomena where when you shine a light on a CD, okay, CD, I'm not sure how many of you still know CDs. I mean, back when I was young, actually, I think CDs were not even invented when I was a child. But you know, very quickly we went through CDs and DVDs and floppy disks and so on. Nowadays, I guess CDs might be more of a thing of a past actually. But it's is this phenomena where you shine a light on a CD and you actually get green, quite special color. Nothing probably to do with photosynthesis, but you know, still green nonetheless. And what happens when you change the angle of the disc is something that's really very rich and nuanced, right? So without further ado, I now invite Myn Jae to tell us more about it, right? And remember, at any time, just raise your hand, type in the chat, and we have this discussion for today, right? Go ahead, Myn Jae, all yours.
Okay, yeah, thanks, Dr. Tan. So, hi everyone, I'm Myn Jae, and yeah, so today I'll be presenting my project, which is investigating the this phenomenon of a colored line appearing on an optical disc under a light source. So, a brief introduction about this phenomenon is actually due to the diffraction and interference of light, which I'll explain later. So, without further ado, let me begin with my presentation. So, Yeah, okay. So firstly, let's look at the relevant parameters for this phenomenon. So for the relevant parameters, we have the incident angle, which is defined as shown in the diagram, the reflected angle, as well as the tilt angle of the optical disc. And then from the top view, we have the azimuthal angle, which is the angle between the line and the camera or the light source, as well as the diffraction constant, which is the patch spacing between the disc. So here are my contents for today. So firstly, let's look at some preliminaries. So here's my experimental setup that I use. So I use a filament lamp that illuminates the compact disc at a distance. And then to capture the color of the line, I use a camera to photograph the disc. And then I also use a black cloth and ensure that this experiment was done in a dark room to block out external light sources. So zooming into my experimental setup, we can see that the tilt angle of the disc was adjusted using optical lab jets and was also measured with a clinometer. So essentially what it does is that because of gravitational force, it allows us to accurately measure the tilt angle of the optical disc. So next, what I did was to characterize the color of the line. So what I did was to pick the brightest from the image from the raw image obtained. What I did was to pick out the brightest points, which was done using computational tracking, and then I fitted a line across, so which allows me to accurately determine the position of the line. And hence, with that, what I can do is to characterize the color across the entire line. So I use the RGB value to characterize the colors, and we can actually plot it in the graph as shown. So basically, what it shows is that it shows the RGB value of the line at like different points of the line. So next, I'm moving to some key observations. So let's say we have a compact disc and we tilt it at 0 degrees. So what we observe is an orange line, and then as we increase the tilt angle, the line will actually turn green, and then it changes to red before turning back to green. So essentially what happens is that as we increase the tilt angle of the compact disc, the line will actually appear to shift upwards, and so it kind of like moves from the red towards the blue spectrum. So like it will move from orange to green, and then it will go back to red again. So as for the DVD, when it is tilted at 0 degrees, we can see that a blue line will be formed, and then when we increase the tilt angle, it turns purple, then to magenta, before changing back to red, and then eventually turning back to green. So this shows that actually that green, like for in the problem statement just now, we see that green line is possible in series and it's also possible in DVDs as well. So next, I'll be talking about how the azimuthal angle affects the color of the line. So if you have an azimuthal angle of 0 degrees, which means that the camera and the light source are on the same plane, then basically what happens is that the color of the line on the compact disc is orange. And then when we increase the azimuthal angle between the lamp and the camera, the azimuthal angle between the line and the camera will also increase. So this causes the line to turn green. And as we further increase the azimuthal angle, it will eventually change to red. And then it can also take on like rainbow colors, which indicates that the color becomes less uniform. So next, at the azimuthal angle of 0 degrees, the line on our DVD is actually blue color. And when we increase it, it turns to purple color, and then it changes to red. And then it will eventually take on more like rainbowish colors as we further increase the azimuthal angle. So this trend actually kind of like follows that of the tilt angle as we've seen just now. So for series, the color will turn from like orange to green, then red, and then orange again. Whereas for a DVD, it will turn from like blue, purple, red, and then back to like bluish color again. So next, I'll be talking about why this actually happens.
Hi, Myn Jae. Sorry, could I interrupt you? I think we're probably not so familiar with the setup. Is it possible to go back to your sort of experiment picture and show us
Yeah.
again what are the angles that are changing? Or maybe another, I don't know which picture is appropriate. Maybe the one where I zoom in with the clinometer.
Oh, this one. Yeah.
You mentioned that the azimuthal angle, which angle would that be now?
For the azimuth, okay, so I think actually we are explaining that later. So like basically the azimuthal angle is like if we let's say we look at the setup from the top view, then we have the incident ray and also the reflected ray going to the camera. So the azimuthal angle is kind of like there's actually like two different azimuthal angles here, but the one we are looking at is the one between the line and the camera. So in this case, the azimuthal angle between the line and the camera is actually half that of the azimuthal angle between the light source and the camera. So basically, yeah, that's what the azimuthal angle is referring to.
I see. So when you said alpha equals to 0, that corresponds to the camera being sort of behind you. You shine the light at the CD, and then the camera is sort of directly in the same line, is it, of
Yeah, yeah.
the light? I see. Right. And then the other angle that you changed, what's that called again?
The tilt angle of the CD.
The tilt angle, that's the one with the two lap jacks, right?
Yeah,
Yeah. Okay. And that one, I see. That one you haven't varied that yet. Have you?
wait, I think I did vary that. Wait, let
Oh,
me check.
okay.
This
Yeah, because I
this one
think
over
definitely
here.
with this 3D kind of problems, it is quite challenging to visualize. So I wanted just to
Yeah,
make sure everyone has the same picture in their head.
yeah,
So beta here is the tilt angle lah.
yeah. It's
Right.
yeah,
So beta is the tilt angle, and then alpha is like the camera angle where you
yeah,
see the light from, and
yeah,
then this one is how you tilt the CD. Okay,
yeah.
cool. Thank you so much. Anyone else has any questions at this point? Okay, if not, okay. Thank you, Myn Jae. Continue from there.
Okay, yeah. So I'm moving on to like qualitatively explain why this interesting phenomenon actually happens. So let's look at the property of the light source. So in this case, I use a filament lamp because like let's say if you use like other light sources such as fluorescent lamps, then we only have like certain wavelength that being emitted. Whereas for a filament lamp, it emits all wavelengths of light. So next I'll be talking about some coherence effects of the light source. So usually diffraction and interference occurs when the light source is coherent. However, in this case, we actually using an incoherent light source, which is a filament lamp. So it's actually, what it means is that each point source on the light bulb, because the light source is not exactly a point source. So what we can think of it as a sum of like infinitely many point sources. And each point source on the bulb actually generates wave planes with varying strength. And also implies that the wave planes have a varying phase shift and coherence length. So what we want is that we need a coherent light for diffraction and interference to occur because we need the phase difference to be the same for conductive interference to occur. So why is temporal incoherence light insignificant in this phenomenon? It's actually because the incoherent rays from different point sources on the light source do not interfere with each other, and hence the object color will actually be the sum of the diffractive effects produced by like each point source. So next I'll be talking about the main reason why this phenomenon occurs. So if you look at the dish from the side view, it actually consists of an outward layer, a lacquer layer, a reflective layer, which is usually made out of like aluminum that reflects the incident light, as well as a polycarbonate layer, which is like a protective layer. So in optical dish, there are actually pitch and lens, which are labeled as shown here. So next, we will investigate the diffraction of light using Huygens principle. So as the light enters the pitch, each point source and the pitch will actually produce secondary spherical wavelets. And the first wavefront is actually the sum of all the wavelets. And because each point source and the new wavefront further produces a spherical wavelet, so we can actually determine the next wavefront from these secondary wavelets. And we can actually repeat this process, which accounts for the wave behavior of light. So next, I'll be talking about the constructive interference between two light rays. So if we have, let's say we have two light rays with wavelength of 500 nanometers. So when the waves are separated by an integer number of wavelengths, constructive interference will occur. So hence, when we add up both waves together, we actually see that the amplitude will increase. So it's like a superposition of two different waves. So moving on, I'll be explaining why we actually see a colored line and not like some interesting defective, like circular defective effects. So if you look at the tracks from the top view, the gray rectangles here represent the tracks. So according to a literature, the width of each plate is around 500 nanometers or 0.5 micrometers, and this is comparable to the wavelength of light because light has a wavelength of between 400 to 700 nanometers. So hence, the incident rays will actually diffract along the radial axis, which is labeled as shown. And then meanwhile, the length of each peak is between 850 nanometers to 3,500 nanometers, or 0.85 micrometers to 3.5 micrometers. And this is much larger than the wavelength of visible light, because the maximum wavelength of visible light is only 700 nanometers. So therefore, the light waves will actually not undergo diffraction, but only undergo specular reflection in the tangential direction. So by combining both effects, this actually enables the incident waves to undergo diffraction and reflection simultaneously, and it allows the incident waves to take many different paths. So next, why does the light only reflect along, like, let's say, one line across the entire disk? So we can actually explain this using Fermat's principle. Okay, wait. I think Kyrie has a question.
Can you hear me?
A bit soft, a bit soft. Can you try again? I can hear a little bit.
Okay, can you hear me now?
Yes, yes.
Okay, so can you go back to the previous slide? Because from our syllabus, what we know is we have the diffraction grating, but
Diffraction
like,
grating, yes.
yeah, so is it similar to that? So like the whole membrane, the dotted line is basically a grating. Is it? Just want to confirm that.
Okay. So Myn Jae, the slide beforehand, I think go back one slide. Okay, this one. So what I understand is uh so okay, how should I put it? Okay, so I think we have to imagine what the CD is like. Okay, so the CD, I mean, uh um my understanding of it is that it has a lot of circular tracks, right? So actually, that's why when you put your CD into the CD player, it needs to spin, right? It spins, and so that the laser that is inside your computer or whatever CD player, right, can sort of shine on the different areas of the track. So what is shown on the slide here, these gray color lines are actually represent the two tracks, and the tracks are sort of separated out by some not sort of like just some plastic polycarbonate in between. Myn Jae, did I get it right?
Kind of. I
Kind
think
of.
it's better if I like draw it out. Yeah.
Okay, okay.
So let me just. Okay. So for a CD, right? Let's say we have a CD like this. Sorry. The drawing is not very good because, yeah, I'm using an online pen. So but it's actually the CD is actually a spiral track. So basically what we have is that, let's say if we look at a small portion over here. So if we look at a small portion, okay, let me just erase this. If you look at a small portion, we actually get those tracks that we see just now. So essentially we get like the tracks here. So like, yeah, we get two tracks. So if we look from the side view, then from the side view we actually get like two like peaks that look like this. So essentially this bump over here is represented by this gray area. And yeah, so yeah, they are represented like this. Yeah.
Okay, so there are these two raised regions, right? And actually these two regions, so is the idea that the light from the two that reflect off these two regions, do they interfere, or is the interference sort of doing track by track kind of
Oh no, it's like, okay, so in this explanation I use two different tracks to just illustrate because it's actually like a waves from different tracks that interfere with each other. However, if we later on as I elaborate later, this effect is actually due to the waves due to light waves from like many different tracks. So in this case, it can be like 50 to 70 tracks, like 50 to 70 light waves that reflect off like the same number of tracks, and they will interfere with each other to form this color line.
okay. So maybe if I hazard a reply to Kyrie's question, right? I would say that, you know, in your normal physics syllabus, you learn about diffraction gratings, which has many lines, right? So many lines. Then you shine the light through this grating, and then the wave that's coming out from each of these slits, you know, sort of interferes. So a similar thing that's happening here would be that all these parallel tracks, I mean, they're actually spiral, as Myn Jae described, right? They're
Yeah.
spiral, but essentially each of them are like if you zoom in, right, they are like long lines that are parallel to each other. And I think these are the ones that will cause that kind of diffraction grating kind of effect to some extent from this situation. Does that sort of make sense to you, Kyrie?
Yeah, thanks.
Okay, great. Thanks for the question. Yes, we can move on.
Okay, so let me. Okay, where did I stop at? Yeah. Okay, so now I explain like why we only see a colored line and not like circular deflecting effects. So okay, we can actually explain this using Fermat's principle. So like I think many of you probably know like the law of reflection. Yeah, which actually states that light travels the shortest path. However, this is like only partly true. So that's actually a more generalized statement, which states that light actually travels the path where the first order where like the derivative is zero. So like let's say if I have a graph of like distance against some parameter, and then usually we want to find like where there's a stationary point. So there's actually three different types of stationary points. So that's like the local maximum, the local minimum, and as well as the shadow node. So essentially, the law of reflection only accounts for the part where the local minimum. It only accounts for the local minimum because at the local minimum, there's a stationary point where like the gradient is zero. But there's also the maximum point as well as the shadow node point, which is not accounted for in the law of reflection. So in this case, we'll be using the Fermat principle as a more generalized statement to account for this. So if we consider a circular track, and then we actually calculate like the distance traveled by the light rays as it reflects off its point, then we can so basically what I did was to characterize like the position of each point on the disk in polar coordinates, which basically in terms of radius factor as well as the angle from the center. So we find that if we actually like do the math, we will find that the light will actually reflect at theta equal to 0 degrees and 180 degrees. And so this suggests that the light rays will actually take this path and it will bisect the azimuthal angle between the camera and the lamp. So actually, I think I'll move on to my mathematical derivation for this part first. I'm not sure if I have it here. Oh yeah. So essentially, we can calculate the distance traveled by the light ray using this equation over here. And then if we take the derivative of this with respect to theta, so we actually get this equation. Okay. Yeah. So we basically set this equation to zero, and by solving for theta, we actually get theta equal to 0 degrees and 180 degrees. Okay, so next I'll be talking about why we actually see different colors across the entire line.
Myn Jae, sorry, if I interrupt you a bit, I thought this was a good point to just check that people are understanding that this is quite doable. So if you go back one slide, or maybe two slides. Okay, well, maybe forward one slide.
Okay, let me just, sorry. Because it's in my hidden slides, it's not
Oh, it's
technically
in the
part of
hidden
my
slides. Okay.
presentation.
Oh, okay. All right. Do you all have a sense? Do you know where this equation comes from? Do you know the square root thing? Anyone has any idea? You can unmute and just shout out. Anyone knows where that comes from? You learn it in secondary school math. I mean, it's sort of like you sort of learn some version of it in secondary school math. Anyone like to hazard a guess?
I would assume it's just.
Sorry, what was that? I couldn't quite hear. Someone said something.
Is it differentiation?
Okay, yes, definitely differentiation. But the first expression, the one that says, distance traveled by light ray equals square root of blah, 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 blah. Where do you think that comes from?
Pythagoras.
Yes, it's basically Pythagoras theorem, right? I mean, so it's a purely geometrical thing. You see, you sort of measure from the light source to the camera, what's the distance traveled, and you can, of course, this one, you do your geometry, right? And you get that expression. So then what Myn Jae was saying is you differentiate that with respect to theta, because theta is that parameter that sort of it changes. I mean, you just change this theta as you go to different points of reflection, right? And then you see which one has where this path has a stationary point, right? So yeah, just to make sure that you connect this with what you have already learned. Of course, this is a more advanced application of it, right? But it's essentially is something that you can follow if you, of course, take the effort to work through the math. It's not so simple as he shown, probably. There's a few more steps, but yeah, the idea is there. Okay, thanks so much.
Okay, yeah. So moving on, then
Kyrie has another raised hand also.
yeah.
Since, yeah.
Hello, I would like to ask what is theta and what is gamma? What these two angles represent?
Okay, sorry, Kyrie, you're really quite soft. Something you asked about what is theta, is it? Or
Yeah, what is theta and what is gamma? The two angles.
okay, what is theta? Okay, theta.
Yeah, define. Yeah.
So okay, if I understand Myn Jae correctly, we are trying to find the path. So in this kind of sort of when you use Fermat's principle, Fermat is the guy with the guy. There's only one Fermat more or less that we all have heard about. He's a mathematician, physicist, and so on. This what you need to do is you measure the okay, we are assuming, of course, light travels in straight lines in space, right? I mean, of course, you can go even more basic and say, oh, why must light travel in straight lines? But okay, let's take it that light always travels in straight lines in free space, right? But even then, the light from this so-called the light source that is drawn over there at the bottom left, right? It could hit anywhere on the disk, and then that means you draw a straight line from the sun to the disk, and then you draw another straight line from the disk to the camera, right? So of course that doesn't necessarily obey the law of reflection, where what incident angle equals reflected angle and so on. But you could just draw straight lines there. Okay, maybe I'm getting this wrong. So Myn Jae, do correct me if I'm wrong. But this is what I think. We draw the straight line and then another straight line. Then you can use Pythagoras theorem to get the length of that two lines, right? Then after that, those two lines are actually parameterized by two variables, r and theta, right? Then you can do the differentiation to figure out for a given r, sort of what is the theta value that will cause the stationary point. Okay, so Myn Jae, did I get anything wrong? If so,
No, yeah, it's about the it's quite correct.
about that. Yeah. Okay, correct. Okay, so hope that helps. Kyrie, does that make sense to you?
I guess.
Yeah. Okay, roughly speaking, so roughly speaking, this Fermat's principle actually is quite an amazing principle. I mean, it's what Fermat said, right, was that let's not say, oh, light travels in straight lines. Let's not say light reflects off mirrors with incident angle equals reflected angle. Actually, what he expressed was a more general principle to say that light always takes the path. Okay, in the sort of early ways of saying it, we always say light travels in such a way that it takes the least time to arrive at the destination, right? So, but if we interpret that using our sort of understanding of calculus and so on, actually it becomes a principle of saying that the path length is a stationary point relative to all other path lengths that are possible. So it's like it's a sort of extremo, it's a stationary point kind of rule. So it's quite unlike things like Newton's laws. Newton's laws, we think, we just say F equals ma, and then that works out, right? But actually there are other sort of interpretations of mechanics where is known as Lagrangian mechanics or Hamiltonian mechanics, where actually the principle is that, let's define something called the action, and then if we extremize the action, we get the classical path. So in a way, Fermat's this principle for light is in that same spirit. Instead of saying there's a certain law or certain trajectory that light travels along, we calculate all possible trajectories, but then we find the one that is a sort of a stationary point. And it's actually, this is quite a very deep principle in physics, actually, because Feynman also, for quantum physics, right, this idea of the action being a stationary point is another way of getting his Feynman path integrals. So again, this idea that, let's imagine that electron can go from point A to point B in all possible paths. So which path did the electron really go? Is the path, at least classically, the path where this call of action functional is actually a stationary point. Okay, I mean, I'm sort of going all over the place, but just trying to give that sense, right? This is probably something that, it takes, of course, a few years of university study and so on. So don't worry if you don't get it now, but it's something that you can look up also if you're interested. Okay, thank you.
Yeah, okay, so I guess I just move on to my next point, which is like basically explain why we actually see like different colors on the CD. So like as we saw in the picture just now, like under like certain conditions, we can actually see like, let's say like rainbow line across the CD, which suggests that the color of the line is not like just one color, but it's actually many different colors. So to explain this, we look at the structure of a camera. So we actually have like an aperture and then the lens to like focus the light. And then behind the lens, we actually have a sensor field with the pixels that basically detect the light. So light from the top and the bottom of the disk will travel into the pixel sensors, which is shown like here. And then because also different parts of the disk actually have like different incident and reflected angles, so they actually produce different colors. So each pixel actually corresponds to a different part of the disk. So basically what happens on the camera is that because basically the different parts of the disk have different colors. So and this different part correspond to different pixels on the camera sensor. So what happens is that the pixels on the camera sensor will detect different colors, which actually causes the camera to observe different colors on the disk. Yeah. So for like the human eye, it's also like a similar thing, except that because in the human eye we actually have rod and cone cells, so they are kind of like the same thing as the pixels that we have in the cameras. So next, I'll be moving on to like quantitatively model this phenomenon. So firstly, we have a Fresnel number, which is given by this simple equation here. So basically what it does is it characterizes whether the setup is in far field or near field condition. So for the far field condition to be satisfied, so you have to satisfy the Fraunhofer condition, which means that f has to be much smaller than 1. And then if it is in the near field condition, then the Fresnel number will be larger than 1. So for my setup, what I did was to calculate the different Fresnel number for between the light source and the disk, as well as between the camera and the disk. And because both values gives me a value that is much smaller than 1, so therefore we can verify that the setup is actually under Fraunhofer conditions, which actually allows us to make use of an approximation, a very useful approximation that I'll be elaborating on later. So let's look at the path difference between two light rays. So from the top view, if we zoom in on the tracks in the disk, so using the diffraction constant as well as the azimuthal angle, then by because as I mentioned earlier that the setup is under far field, so we can approximate both lines to be parallel to each other. So in this case, by using trigonometry, we can get the path difference between the two light rays, which is given as shown here. And then moving on, what I do is because I transfer the d cosine alpha to the track spacing, which is, and then now we are looking at it from the side view. So we can also approximate the incident rays to be parallel because of the far field condition. So we can calculate the path difference again using trigonometry. And then we also have to account for the path difference by the reflected rays, which is shown as such. So with that, we can get the total path difference by adding the path difference from the incident and the reflected rays. And this allows us to form the diffraction equation in the disk. So essentially, we are replacing the path difference with these two variables here. So kappa, which is the k symbol here, it represents the order of diffraction, which is basically an integer. And then we also have lambda, which is the wavelength. So as mentioned earlier in the qualitative explanation, constructive interference occurs when the path difference between the two light rays is an integer number of wavelengths. So therefore, in this case, the kappa is basically the integer number and then of the wavelength. Yeah. So for the optical disk, we can set like some boundaries here. So we can define the incident angle to be positive all the time, and then the reflected angle can be between 0 to 90, between negative 90 to 90 degrees. So if the reflected angle, in this case, we if the reflected angle is on the other side of the incident angle, then we call it to be negative. So next, let's look at like some let's look at like how the peak wavelength that undergo conductive interference will depend based on the incident angle of the disk. So in this case, each line here represents a different order of diffraction. So and then we also see a similar trend for the DVD. So to explain why, we can explain this from the path difference equation. So as we increase the incident angle, we can see that because we limit the incident angle between 0 degrees to 90 degrees. So essentially, what happens is that because the sine factor from 0 to 90 degrees is strictly increasing. So when we increase the incident angle, the path difference will also increase. So because the path difference equal to kappa multiplied by lambda. So I think yeah, so okay, sorry, just a bit of technical difficulties. But basically, after the path difference increases, then the wavelength, which is the lambda, will also increase. So basically, a longer wavelength of light will conductively interfere. And then let's look at how like the reflected angle changes the wavelength of light that interfere. And this for CD, and the graph before was for CD, and this is for DVD. So from the path difference equation, we can see that when we increase the reflected angle, the path difference will also increase. So using a similar principle, the wavelength of light will also increase. So next we'll look at the third angle. So it's the third angle. If we increase the third angle, like if you imagine it, the incident and reflected angles of the incident and reflected light waves will decrease. So from the path difference, we can see that as we increase the third angle, the incident angle and the reflected angle will also decrease. So because both are in like the sine function, and when the values decrease, the sine function of the value will also decrease. So therefore, this causes the path difference to decrease too, and hence you will result in light reflector wavelength to conductively interfere. And then we also see that the wavelength is also negatively correlated with changing like the azimuthal angle in CDs as well as in DVDs. So to explain this, we can also use the path difference equation again. So as we increase alpha, but this time because alpha is in the cosine function, so the cosine function is strictly decreasing when alpha is from 0 to 180 degrees. So when we increase alpha, the cosine function will decrease. So this causes the path difference to decrease also. So therefore, the wavelength of light that conductively interfere will also decrease. And then lastly, we also have the track spacing, which is basically the distance between the tracks in the optical disc. So when we increase the track spacing, the path difference will also increase, and this causes a longer wavelength of light to actually conductively interfere. So next, I'll be moving on to explain like how the color changes depending on the different angles. So let's say if we increase the third angle of the disk, so therefore the incident and reflected angles at both sides of the disk will actually decrease. So therefore this causes the wavelength of light to decrease also. So what effect this actually has is that it causes the colored line to appear to shift upwards on the disk. And then we can also explain like why the color becomes like less uniform, like we see like more rainbow colors when we increase the third angle further. So when you increase the third angle, the difference between the incident angles will at both ends will also increase. And the same also applies for the reflected angles. So because of these two factors, and also the third factor is that the rate of color change also increases with the third angle. So like the rate of color change is essentially represented by the gradient of the graph as shown. And then so because of these three factors, the line color will actually become less uniform because there's like a steeper gradient. So there is a greater like change in color as we increase the third angle. And then next for the azimuthal angle, when we increase like the azimuthal angle, the wavelength at both ends will also decrease. So this also causes the same effect of the colored line appear to shift upwards. And then also at both ends, the difference between the the difference between the azimuthal angle should also increase as we increase like the overall azimuthal angle. So also from the graph we see that the rate of color change also increases with the azimuthal angle. So this causes the light color to become less uniform as the azimuthal angle increases. So from the wavelength, so now that we can calculate the wavelength of light that will undergo constructive interference. So next what we do to actually get the color of the line is to border the intensity. So because even though we have let's say like 3 different wavelengths of light, but not all these wavelengths have the same intensity. So let's say if I have a red light with very strong intensity and a blue light with very low intensity, when I combine them together, it doesn't give me like a magenta colored light. So essentially, because the red light has such a strong intensity that it like overpowers the blue light. So essentially, we more or less see a red color light. So that's why it's important for us to model the intensity of the light. Yeah, wait, Dr. Tan, do you have a question?
Okay, great. I think this is a good time to pause a bit and sort of see where we've gone, because Myn Jae has just shown us a lot of slides. But I think what I hope that you have seen is basically he's saying, we start with the theory, right? The theory about whether all those Fermat's principle and the diffraction, the path difference is quite like what you learn in H2, right? Where you talk about the path difference between two waves, and then what's the condition for constructive interference when your path difference is actually an integer wavelength, or if destructive interference if it's a half integer wavelength, and so on, right? So from that actually is such a powerful model already, because from that you get all the conclusions that he was getting. You can vary the azimuthal angle, you can vary the what you call it, the tilt angle, so all those graphs that he's showing basically is saying with that one theory, if I look at the phenomena by changing different parameters, I can actually predict where our what I will see in the lab, right? So that I think is the main picture. I mean, even if of course it's hard to follow all the different detail because it's so many things that you could change, right? But the idea that with this one model, you can actually change different things, and then that is great for science, because you can use you can then test your prediction against all the variety of experiments, right? Which I think is sort of also one of the next sections in his presentation, where he will actually measure things, then do what he was describing about taking the picture with a camera, then using pixel counting or whatever, to figure out where the line is, what color is, and so on, and then seeing how close a fit the experiment is relative to the theory. Okay, there happens to be also a question in the chat, which Kyree directed to me, but I suppose he was trying to ask whether imaginary numbers are used. And yes, if you look at the current slide, which Myn Jae is probably going to expand more, is complex numbers. Now, complex numbers you might learn in H2 math, right? And then you wonder, why am I learning complex numbers for? Why am I learning imaginary numbers for? Of course, there are people who say, actually, these words, I mean, what's a real number? What's a rational number? I mean, these are all descriptions. Doesn't mean that imaginary numbers are really that imaginary. Actually, imaginary numbers are very useful in science and math because of well, it's not Taylor Swift, but Taylor series. Okay, in the sense of actually more okay lah. I mean, I say Taylor Swift, but not totally. There is more the more Euler representation, right? E to the I theta is actually cosine theta plus I sine theta, right? So those of you who have learned some complex numbers, you might have heard of identities like that. Basically, complex numbers help us to convert exponential functions or relate exponential functions with trigonometric functions, which is very useful because when we study waves, normally we are studying trigo functions, right? But we know that trigo functions, when you differentiate it, when you integrate it, it changes back and forth, right? From sine, you differentiate, you get cosine, but you differentiate cosine, you get negative sine, and all those kind of things. Whereas exponential functions, you differentiate, exponential, you get back exponential. So it is mathematically convenient, right? But there are also other reasons, I guess, where it really just cleans up this representation of waves using complex numbers, right? So I will pause here my comments and let Myn Jae continue on with this idea of using phasors for light.
Okay, so as Dr. Tan mentioned just now, using imaginary numbers is actually quite a useful method here because each wave is like different. It actually can be represented as a sine wave or cosine wave depending on how you think about it. And what if you want to get a total intensity, we have to like add up these waves together. So let's say if I have like if I'm trying to add up a multiple sine waves together, it's not going to be very convenient. So therefore, it's more convenient to actually use it's more convenient to use imaginary numbers here because you can actually make use of the exponential like the exponent laws to actually add up all the or like add up multiple waves together more easily. So in this case, what I did was to characterize the electric fields of the two light waves which are given by the general wave equation. So because we are comparing two waves which have the same wavelength and therefore they also have the same frequency. So therefore we can ignore the time dependent term. And also because both waves are produced by the same point source and because both waves to undergo conductive interference, they have to be coherent and therefore they have to be produced by the same point source. So therefore the phase difference between the two waves has to be zero too. So if you look at two different light waves, so the formula as mentioned just now, the formula to describe the electric field of the light waves is labeled as shown here. And yeah, so by adding up together and by using some algebraic manipulation, which are shown later on, we can actually apply the relationship between the intensity and the electric field. So essentially, the intensity is equal to the is equal to the sum of the electric field square. So yeah, if we apply the geometric series, we can also obtain the equation for the light spectrum. So I'll move on to the full derivation first. So if let's say we have, because we know that the path difference is equal to this expression which has been derived earlier. So by taking by let's say we have light wave at position n, and we can write the electric field of that light wave which is given by shown, and we just rearrange it slightly using the exponential rules. So to get the total intensity, we have to first get the sum of all the electric fields. And to get the sum of all the electric fields, we can apply a bit of algebraic manipulation over here. And then afterwards, you can use the geometric series for exponential functions. And then by using some substitution, I think I'll just pause a bit here for everyone to understand. So by using like some substitution, we can basically like get this equation over here. So it's not really much. It's just like the normal exponential rules that you use in school. And then lastly, lastly, because if you see here that the part that is not in the fraction is actually proportional to e to the part is actually proportional to I0. So like if you want to put in I0, we have to square it. So we have to square this entire thing, and then we sub the portion that is not in the fraction with I0, and the part that is in the fraction we simply just square it to give us this equation over here. Okay, then let me just go back to my previous slide. So after that, from here, basically we have to convert the intensity spectrum into the color. So for the intensity spectrum, we will look something like this graph over here. So like this is how it changes depending on the third angle. So like the intensity spectrum, which is basically intensity against wavelength, will also change. So to convert this into the color, what I did was to multiply this with the response curve of the camera. So the response curve of the camera actually represents how sensitive the camera is to like different wavelengths of light. So for example, let's say in the graph on the left, let's say if we look at when the wavelength is around 600 nanometers, then we see that there's actually a peak in the red color curve, and this red color curve represents the red R value that the camera actually observed. So this suggests that because 600 nanometers is like red light, so therefore what it suggests is that the camera actually sees a a lot of weak color when we shine 600 nanometer light into it. So basically to cover like the intensity spectrum just now, like we look something like the graph on the right. So basically what I did was to multiply with the respective RGB curve of the response curve, and then after that we take the area under the product of the function. So basically then what I did was to normalize the RGB values because it is quite intensive to get the actual intensity. So what I did was to get the normalized intensity, which is given by this equation as shown. So for the simulation, we can using this model we can actually predict like the color as we change like the third angle. Yeah. And then let the video finish running first. Yeah, and also for the same also applies for the DVD. So you see like it changes from a blue color to purple color, then red color, and so on. So you also notice that if we increase the third angle, the graph will also like appear to shift towards the right. So it also corresponds to the line appearing to shift upwards. Yeah. So next I'll be moving on to my experiments. Basically like comparing the theoretical model with the experimental data. So firstly what I did was to measure the touch spacing between the touch on the optical disc. So how this was done was actually using a helium neon laser. So basically I defined my variables as such, and then if you look, what I did was to place a white dot behind the laser. So because of like the simple diffraction gradient equation, we can actually measure the touch spacing of the optical disc. So I defined x1 to be the distance between the spots produced by the zeros and the first diffraction order, and x2 is the distance between the spots produced by the zeros to the second diffraction order. So I can use this equation over here, which is basically a modification of the simple diffraction gradient equation, and I can use this to calculate the diffraction constant. So here are my results for the diffraction constant. So like for CD is approximately like 1.493 micrometers, and for DPD is around 740 nanometers. So firstly, let's look at how we change how like the color changes with the third angle. So the red dots here represent the experimental data, and the solid lines represent the predicted color based on the theoretical model I presented earlier. So we can see that it's actually quite a good fit, which suggests that the theory is actually quite accurate. And then as you increase the third angle, we can see that there's also a good agreement. Okay, yeah. Okay, so now moving on, we'll look at like how the changing of third angle will adjust like predict the color of the line on a DVD. So like initially the color is actually blue color, and then as we further increase the third angle, it will actually become like a red line, and then it will eventually change to a green color line, and then after that it becomes a blue color line again. Yeah. And then next we'll look at changing the azimuth angle for ICD. So we still firstly object the orange line, which turns to green color, then red color here. Yeah, and then afterwards it becomes like more rainbowish color. Like as you can see, there's like many different colors. And then lastly for the azimuth angle for DVD. So initially the color of the line is like blue color, and then it turns to like purple, then red. And then yeah, it also follows the similar trend to the CD. Like the color across the line becomes less uniform, which basically becomes more rainbow. So next I'll be talking about some further insights. So we can also like calculate like the relative brightness of the line on the optical disc. So because you know that the relative intensity is proportional to the sum of the normalized RG and B values, and then we can also apply the inverse square law, which is basically suggests that the intensity of light decreases like inversely. It is like inversely proportional to the square of the distance between the light source and the point of the observer. So we can also like somewhat theoretically model the relative brightness across the entire line. So yeah, that's pretty much it. Yeah. So yeah, that's pretty much the end of my presentation. Thank you.
Great, thanks so much, Myn Jae. That was awesome. Maybe can I just bring you back to the very, very simple one where you measured using the ruler and those
yeah.
spots, the CD and the DVD. Just to make sure that we link it. Yeah. So for this one, right? When you have the results on the next slide, is it okay? Maybe okay. Just the picture first. You're so experimentally, what you get is that the DVD deflects it less. Is it? There's less of that deflection.
Yeah.
In terms of angle.
Yeah.
Which suggests that the wavelength. Sorry. Okay. So meaning to say for the same wavelength, the sort of fringe spacing is smaller lah.
Yeah.
Right. And that as a result, we conclude that the effective sort of length scale or the distance between your slits, I mean so-called slits or pattern in the DVD is actually smaller.
Yeah.
Right. Yeah. Okay. So that is one at least very basic thing that we can link to of course H2 kind of content. I noticed also as you were showing, I mean, there were certain graphs where of course there's the data was actually quite rich. It seemed to be that there's all sorts of curves happening in the
Yeah.
data versus the experiment prediction is quite a smooth line.
Yeah. Sorry about here. Yeah. Where are these?
Especially there were some oscillations or so on.
Let's see if I can let me just sorry, wait, let me just change the slide because I think I have like automated animation, so let me just
No
change
problem, no problem.
for a moment. Let's say for this one, let me just put this. Let me just share my screen again. Yeah, over here.
Okay, loading. Okay. Yes. Like let's say for this one, right, the blue one. Well, I guess this is still quite small, right? But there were maybe some where it was a bit more obvious, or maybe actually not really that obvious lah.
Sorry, I think I'm not
Yeah.
sure by a bit of technical difficulties. Yeah.
No problem. But will you have any? Is there any broad comment that you could make regarding that slight difference? I mean, it's only very slight lah, of course.
Yeah, I think the slight difference is probably like due to experimental error, like because there's really like a lot of characterization done here, so that's like wait, let me just go back to
Right.
the slide.
Because especially I mean, even the simple matter of taking a photo, right, is not so straightforward because you have to assume that the camera behaves in a certain way, right?
Yeah.
The camera's response function to the different colors of light actually is something that is quite unique and specific to the camera. And do you sort of rely on the manufacturer's sort of characterization, or is it something that you independently have had to measure for yourself?
This was independently measured by myself, so that's probably like some error.
I see. Yeah, because
the
the manufacturer probably won't say all these things, right?
Yeah.
So you actually have to use different kinds of light and then measure. Okay, you change the wavelength. You change the wavelength of some monochromatic light, and then you see how many how much intensity is developed by the camera. Yeah. It really reminds us that all these optical things actually, especially when you deal with visible light and so on, there's actually our eyes see a certain thing, but the camera of course has to be calibrated in its own way as well if you want to be very quantitative about it. Ken, I think at this point let's invite questions. Anyone has any questions, just raise your hand. I mean, I'm sure there's all sorts of interesting things that you notice along the way. Feel free to direct us back to the start of the presentation or whatever slide you sort of remember. We can discuss it a bit more. Yeah, it's quite a cozy number of us here in this room, so don't be shy. Any questions, anyone, or comments, or something that it reminds you of? Doesn't have to be sort of exactly about the details, or certain areas of the presentation you wanted to get the big picture understanding. That's also fine. Anyone? Or I mean, a simple way is, of course, I can just go around, give everyone some airtime. I'll start with the people who I can see lah. Okay. Guan Yu, do you have any questions or comments that you wondered about as you were listening to this presentation? Oh wait, sorry, did you say something? No, is it you said no probably?
I say no.
Okay, Ken, thanks. If you do have any, of course, feel free. How about Alicia? I hope I pronounce your name properly.
No questions.
No questions. Okay. Yeah. All right, no problems. Adeline, how about Adeline?
No problem.
No
Thank you.
problems. Oh, very clear. Okay, great. Yes. Yeah, I of course it is. Yeah, really impressive work. I mean, if you really think about. Okay, so Myn Jae, like just get a sense. How long did it take you to do this project from like sort of start to finish? I mean, how long do you think you spent sort of working out the theory, working out the experiments, and so on?
I
Do you
think
have
probably
some?
like 7 to 8 months. Yeah.
7 to 8 months, right?
Yeah.
So yeah, as you can see, really impressive work. I mean, from setting up the experiment, of course, like so much data to take, right? Every single graph you see, don't forget there's so many points. I mean, I guess there's of course a lot of these points, no, actually every single point, if let's say the horizontal axis is actually the length, right? Yeah, I don't know. I mean, it's probably a lot of actually work to get every single data point. And as you can see, has so many graphs. Yeah, and not to mention, of course, the understanding the theory, which is not simple in itself. Yeah. Okay. Next. I know. I mean, Lily is my colleague, so she might not probably have questions at this point. Joshua. How about Joshua? Joshua Chu.
Oh, hi.
Hi. Any?
I'm a
Yeah.
bit slow on catching up. So it's
No
like,
worries.
can
No
I just
worries.
ask what is the difference between a CD and a DVD that cause the difference in results? Is it like the structure or like the material used or anything?
Myn Jae.
Yeah, that's a good question. So basically, right, if for the CD and DVDs, they're actually like this bump over here. So for CD, the distance between the two bumps is actually much longer, like 2 times longer than that of a DVD. So that's actually like the structure difference that actually causes this like difference in the phenomenon.
Okay, thank you.
And so Myn Jae, other than this structural difference, I mean, okay, so of course I'm of that era where I know a little bit about DVDs and CDs because we were using these for data storage and so on. I think CDs can store something like 700 megabytes of data, so to speak.
Yeah.
And then DVDs normally is like, I think what 1.4, 1.5 gig. So
Yeah.
almost double lah. So
Yeah.
that I guess seems to, I mean, quite nicely corresponds to sort of like double the size of, you see, if you're, so those like little bits, so like patterns in your CD or DVD, right? Those are the ones where you can actually store your data on, right? So if you have sort of twice, I mean, if the spacing is half, then I guess you get twice as many. Okay, I of course there's the whole thing that there's the area. It's not just area, but it's area and length also lah. So I suppose it's maybe more complicated than that. But that spacing between them, I think if I'm not wrong, the kind of laser that you use for your CD and DVD is also different, right? So those drives, right? Those optical drives that use CD, that can read CD and DVD. I think they might even have to have two lasers inside, right?
Yeah.
Yeah, because in order to get a proper to get the maximal sort of data out of a DVD, you probably need a shorter wavelength laser than if you were using a CD lah. Yeah. Then there might be, of course, differences in the dye and all those kind of chemistry aspects, but I think that is not so critical for that doesn't factor in your explanation, right, Myn Jae? Does
Yeah.
that? Yeah, it's really just a reflection. We just treat it like a mirror. I mean, okay, I mean, sort of like a mirror, lah, right? In that sense.
Yeah.
Okay, great question. Let's see, where am I now? Yiwen, do you have any questions, comments?
I have no question.
Okay, cool. Next one. Okay, this name I hope I pronounce it properly. Zomo Kyang. Yeah, I don't know. Sorry if I pronounce it wrongly.
Yeah, I have no questions.
No questions. Oh, okay. How about Rachel Chan?
No questions.
Okay. How about Michael next? Michael NK.
Not much questions, although I was kind of like lost after the part about the key observations.
Okay, the key observations. This was so the theory part you could follow. Which I mean, yeah, we could give a. Okay, I think of course it's really hard to follow in detail technical presentations like this, right? But I think if there are certain points of the sort of key observation. Okay, so Myn Jae has the slide there, right? So sort of here.
I mean, I just only like just see. What I meant was actually like after this one, I suddenly got lost after this because I was kind of a bit distracted on things.
Yes, understand, of course.
But I think I kind of understand a bit from like how say a bit like the superposition part, the interference. Yeah.
Okay, great. Yeah, it's a very rich problem, lots of interesting physics that all comes together actually to try to explain this. Okay, great. Amanda Ting.
No question.
No questions. Any comments?
No.
Okay, thanks so much. Okay, this one. Tejaswi. Is that your name?
Yes. No questions.
No questions. Okay. And Zun. Sorry, I might have mangled your name. Sorry about that.
Sorry, no questions as of now. Thank you so much.
Okay, no questions. Great.
Sorry to interrupt. I have a question.
Yes. Okay, Guan Yu. Yes.
Why is it always changing to?
Sorry, it's a bit hard to hear you.
Sorry. Why is it always changing to a contrast color when it's like red to green?
Okay. I heard. Why is it something color red? Okay.
Why is it changing to a contrasting color, like from red color to green color?
Okay. In this current slide, right? Let's say we have this current slide. Okay, so Myn Jae, maybe you make this full screen on
Sure.
on this current slide. Yeah, now that we've had the benefit of course explaining running through the whole presentation in some detail, it's actually true. It's quite worth going back to the start again, right? These qualitative observations. Like okay, let me try to understand this angle of incline. So this one, what is being varied is the beta. So beta here is the tilt. Remember the two sides where you tilt the CD towards the light and so on. So that's what's happening. You are tilting the CD towards the light. I recall towards the end of his presentation, there were some pictures where you draw a light beam hitting one end of the CD and the other hitting the other end. And he was saying as you tilt it more, actually the difference in the angle increases, right? That means if it was totally flat, the angles on both sides are roughly the same, right? Whereas if you tilt it more, then there's more of a difference between the two ends. So with that, you expect that let's say the 30.5 degrees here, right? The second one from the right, the light that that diffracts off the top part versus the light that diffracts off the bottom part. I mean, remember always there's this annoying hole in the middle, right? I guess without that hole, maybe you get more. Yeah, of course you get more interesting data from that central region. But because CDs always come with that hole, basically the top part is a different color from the bottom part for all the reasons because the angle is different, I suppose. I mean that is my sort of simple explanation. Not sure, Myn Jae, you want to add anything to that?
No, I think yeah, quite good explanation.
Okay. So yeah, Kwani, hope that explains it. And whereas for the smaller angle, yeah, as you can see, as it's true, right? If you look at this picture here, there are 6 pictures. From the left, the first one, yeah, orange on both sides, right? The second one, okay, green on both sides. Then the third one, you start seeing, okay, the color is a little bit different, right? A bit more yellowish on the top, a bit more orangey on the bottom. At least, I mean, that's in terms of how I describe colors, right? Again, color is another perception thing that is quite nuanced actually. And then really the second one from the right is when you have really very obviously different colors, at least visually, right? And that's coming from as the tilt angle increases, you get much more of that difference, and therefore those equations you solve, basically the constructive interference, the wavelength at which you get constructive interference is quite different, whether at the top or at the bottom. And that therefore the color that the camera detects or our eye sees is quite different. I guess this one is a camera picture, right? The camera image. Okay, great. Any other questions? Anyone else? Otherwise, yes, I think thanks so much for coming by. Hope you found this enriching and enjoyable. I certainly did. I certainly learned much more about this. I know, of course, this I did see a presentation on this IYPT problem, but the challenge, of course, for such a complicated project, right, is that when someone tries to explain to you in 10 minutes, is you really only just get the very superficial understanding. Like, here at this time, having 1 hour plus to actually discuss and also ask questions and also interact and trying to understand it myself and explain it myself, I think it really helpful with Myn Jae's guidance, right? And so if you enjoyed this session, please remember to also look at our website so that okay, I should probably sort of try to type it into the chat, right? Give me a second, copy, paste. Okay, you probably know by now our PIES website, right? The Physics Innovation and Exploration series. So for this year, we have a couple more talks lined up, right? In a similar spirit as today's one. And I am also asking some other previous IYPT, OYPT participants if they can share also. So depending on the schedule, we might have more than 3 talks this year. But yeah, so thanks so much. Keep in touch. All the best, and enjoy. Hope you continue enjoying physics wherever you are. Right. If no other questions, join me again in thanking Myn Jae for this wonderful session, and take care, everyone.